My name is Guowei and I'm from Group 2, and today I would like to present the application of second order differential equations in electrical circuits. So what is the second order differential equations? So here's about a little introduction about the second order differential equations. So a second order differential equations is a mathematical equation that involves the second derivative of an unknown function. It represents a relationship between the functions, its first derivatives, and its second derivatives. The general form of a second order differential equations is something like this. As you can see, there are a, b, c are constants with a function fx here. And you have a y double prime, which is the second derivative, and y prime, which is the first derivative, and y, which is no derivatives at all. So here's about a general formula. This is the general formula of a second order differential equations. So now we have to understand about the general information about the second order differential equations. So what are the applications? What can we do to second order differential equations? So second order differential equations is proven to have practical applications in many aspects of your life. They serve as a very powerful mathematical tools to understand and analyzing dynamic systems. So by understanding the relationship between a function and its derivatives, a second order differential equations can be used to predict and model the behavior of a certain complex phenomena. So these equations have applications in fields such as physics, engineering, biology, and economics. The ability to mathematically describe the secondary behavior of systems allows us to optimize designs, control processes, analyze vibrations, predict the motions, and explore the fundamental principles underlying many natural and man-made phenomena. From understanding the motion of celestial bodies to analyzing the electrical circuits that power our devices, the second order differential equations plays an important role in shaping our understanding of the world around us and driving technological process. So here are some examples of application of second order differential equations. So there are three main applications. The first one is the classical mechanics. So in physics, in dynamics, we can play the crucial role by describing the motion of the objects under the influence of forces, such as the Newton's second law of motion, which relates the force acting on an object to its mass and acceleration. Can also be represented as a second order differential equations. The second one is about electrical circuits. So the second order differential equations, it can be used to model the behavior of electrical circuits, such as capacitors, inductors, can analyze the transient responses, the frequency, the circuits, so that enable the electrical engineers to design and optimize the entire electronic systems. The third thing is about vibrations and oscillations. For example, pendulums, springs, and mass spring systems. So these equations can help us to determine the natural frequencies, the damping effects, and amplitude, longitude, and also the wavelengths of the oscillations of the entire systems. So in this presentation, we will only focus about electrical circuits. So let's take a look at the circuits. You can see there are two circuits. This is the direction of the current. There's a capacitor. There's a resistors, transistors, and there's a voltage supply. So you're looking at the second order circuit, and it also can be described by using the second order differential equations. So they usually have inductor, capacitors, and resistors linked in either in series or parallel. So I is the current in the circuit and Vt is the input voltage signals. So it also represent and describe the effect of inductance, resistance, and capacitance on currents and voltage in the circuit. So in this circuit, they are in series. All these series are in series in a voltage source. So they can be substituting by using the Kirchhoff's voltage law, the KVL. So we can get the voltage at the voltage level at the resistor, the voltage level at the capacitor, the voltage level at the inductors. If you add all these three together, you can get the total voltage of the entire electrical systems. So here is by substituting this, the formula, and then we integrate it into the equation above, we can get these equations. This equation is important because we're going to use it in later applications, and it can be applicable only when the source is an unchanging voltage, which means the voltage remains the constant and it doesn't change at all. So here's the example. So let's say there is a circuit has an electromotive force ET, has total of 150 volts, and 10 ohms of resistors, inductor of 1 Henry, and a capacitor of 1 over 1900 farad. So let's say the initial current is 0, and the initial charge is also on the capacitor are also 0. So find the change on the capacitor at any given time. So based on this equation, we can get a lot of information. ET is 150 volts, the R is 10 ohms, L is Henry, the capacitor is 1 over 1900 farad, and the initial current is 0 when the time is 0, and initial charge, which is also 0. So they want to find the charge of the capacitor at any given time. So remember this equation. So this is the general formula of the equations, and you plug in the value inside, and then you get these equations. So notice at the ET, the ET is 150. So we can say that this equation is non-homogeneous differential equations. So what are we going to do to solve it? Well, we have to separate it. So first thing, we only solve these equations. We can solve it by using characteristic equations. By using simple quadratic formula, you can get the value, which is -5 plus minus 25 mod sub 3i. So take a look at this equation. This is something related to a complex number, and then you plug into the value. This is the general formula. You put in the value, and you get the QC. And then when we are trying to do the QP is something like this. And then you can say that by using this characters equations, and then you integrate it. Make sure there's no similar terms when comparing to these equations. And then you integrate 2 times. You differentiate 2 times, you get a 0, and then you substitute back into these equations, and then you should get the constant. The constant is 3 over 38, which means the QP is 3 over 38. So since you already find the QP and the QC, so we can find the general equations. The general equation is QC plus QP equals to the final formula, and it looks something like this, which is e to the power of -5t multiplied by a sine 25 sub 3t plus b cos sine 25 sub 3t and plus 3 over 38. So this is the general formula, but it doesn't stop here, because remember the information given. So let's say the initial current is 0 when the time is 0, and you put it inside the value inside there, and you should get the equations. So we can get the A is -3 over 190 sub 3, and you place it into the value, and you place it into the value here, and you get the equations. So that is all for our presentation, and I hope you like it, and thank you for lending me your ears.